Hi everyone, we're going to continue with our Chapter 4 homework problems. Here is number 5. Zinnia has a mass of 85 kilograms. What is her weight in newtons? Now remember, weight is a special case of force of gravity. So weight is nothing but mass times the acceleration of gravity. So we're going to take 85 kilograms times the acceleration of gravity, 9.8 meters per second squared. And when we multiply 85 times 9.8 meters per second squared, I end up with 833 kilogram meters per second squared, and a kilogram meter per second squared is a newton. So her weight is in the metric units, will be in newtons. Number 6, Clyde weighs 1,120 newtons. What is his mass in kilograms? Well, mass is kilograms. Weight, remember, is force of gravity times mass times acceleration of gravity. We're going to look for mass. To do that, we're going to have to do a little algebra. I'm going to divide both sides by acceleration of gravity to get mass alone. So mass is going to be equivalent to force of gravity divided by the acceleration of gravity. So this is going to be 1120 newtons divided by 9.80 meters per second squared. And when I do that, I'm going to end up with 114 kilograms. Now, where do those units come from? A newton is a kilogram meter per second squared divided by meters per second squared. So you invert and multiply when you divide by something. So second squared over meters. Meters cancel meters. Second squared cancels second squared. We end up with kilograms, which we do, and life is good. Next problem is a little trickier. Less and less money is being spent on manned spacecraft, so astronauts in the future will need to use some common household tools. In some future time, Zeppo the astronaut travels to the planet Xenon to determine the acceleration of gravity on Xenon. He weighs himself on his trusty bathroom scale. On Earth, Zeppo weighs 185 pounds. On Xenon, Zeppo weighs 215 pounds. What is the acceleration of gravity on Xenon in meters per second squared? Now, this problem can be done a couple different ways, and it can be a little bit easy or it can be multiple steps. So I'm going to do it two different ways, and first off, I'm going to do it easy but with a little bit of logic. And some of you will follow this and some of you are not going to like this at all. But here's the logic. Because of the fact that weight is directly proportional to the acceleration of gravity, we can make this logic. We can say that somebody's weight on the planet Xenon is going to be equivalent or related to their weight on the planet Earth. And since we know that weight is related to or proportional to their acceleration of gravity on Xenon, which is proportional then to the acceleration of gravity on Earth, this is not necessarily a mathematical equation, but what it is logic. Weight is proportional to weight, and gravity is proportional to acceleration of gravity. So if I do a little algebra here, and I solve for acceleration of gravity on Xenon, acceleration of gravity on Xenon then is going to be equivalent to the weight on Xenon times the acceleration of gravity on Earth divided by the weight on Earth. Now, if I do that, the acceleration of gravity on Xenon is going to be equivalent to the weight on Xenon, which is 215 pounds, times the acceleration of gravity on Earth, which is 9.8 meters per second squared. And right now, some of you are having kittens because you're going, Mary, you're using metric units. Yeah, I know. And then weight on Earth, which was 185 pounds. As long as the units work out, we can get away with all kinds of craziness. Pounds cancel pounds. We're just looking at a proportionality. And if I do this, I end up with 11.4 meters per second squared is the acceleration on Xenon. Now, that is one way to do it, and some of you right now are giving me the fuzzy eyeball and saying, I don't like that at all. So let's try this a slightly different way. And I know I'm going to need some space, so I'm going to erase If you didn't catch that, hit rewind on the video, and here goes nothing. Now here's another way that you can go about it. Mathematically, you can go about it this way. You can say, okay, so if he weighs on Earth 185 pounds, we can say what does not change when you go from place to place, weight or mass? Mass. Mass always stays the same. So force of gravity is mass times acceleration of gravity. So if we find his mass on Earth, his mass is going to be exactly the same when he goes to xenon. So how are we going to do this? Well, it's going to take a couple steps. First thing I'm going to do is I'm going to take those 185 pounds and I'm going to convert that into I am going to convert that into newtons. Now there are, if you look on your conversion table, there's 4.45 newtons per 1 pound. Now if I do that, I'm going to end up with 957 newtons that this person is going to weigh. And then in order to find his mass is going to be his weight, or the force of gravity on him, divided by the acceleration of gravity, 957 newtons, divided by 9.8 meters per second squared. So, 957 divided by, did I do something wrong? I think I messed up. Did I mess up? 185. I was using old numbers. Never trust old numbers. Let's just do this fresh so Mary doesn't do silly stuff. Okay, 185 times 4.45. What do we have? 823 newtons. Okay, so 823 newtons divided by 9.8 meters per second squared. So on Earth, 823 divided by 9.8, this person is going to have a weight of 84 kilograms. That's going to be this person's mass. This guy's mass is 84 kilograms. Okay, now if that's going to be his mass, we have to find his, we're going to have to find his weight on xenon. So his weight on xenon is going to be, if he weighs 215 newtons, convert that from pounds, convert that from pounds to newtons. There's 4.45 newtons in 1 pound. 1 pound. That's going to be my 957 newtons. And so if that is his weight, or the force of gravity on him on xenon, okay, this is his force of gravity, that is his mass. We know force of gravity is mass times acceleration of gravity, so the acceleration of gravity on him is going to be the force of gravity on him on xenon divided by his mass, or 957 newtons divided by 84 kilograms, and when you do that, you end up with 11.4 meters per second squared. Same number we got before, a little bit more fussing around, but some of you that might make more sense in your brain. Okay, let's call it quits and we'll come back and do some more next time.